This video is the second half of our introduction to series and convergence. If you have not yet seen the first half, you should do that now and then come back to this video. You can either click the link that appears in the upper right hand corner or find the link in the description. This is the practice video, so I'm going to run through some examples under the assumption that you already know the basics. Problem number 2. Find the sequence of partial sums S1, S2, S3, S4, and S5. We traditionally label individual terms with the letter A, so this is A1, A2, A3, A4, and A5. This is an infinite series. You can tell because of the ... at the end. S5 is what we call a partial sum. In this case, it's the sum of all of the terms up to and including the fifth term. Similarly, S4 is the sum of all terms up to term 4, S3 is the sum of all terms up to term 3, and S2 is the sum of all terms up to term 2. S1 is just the first term. By the way, let's assume this is all on the non-calculator part of the test. So put your calculator away. You might have to do a little bit of middle school arithmetic along the way. I already mentioned that S1 is just going to be the first term. So that is 1 over 6. S2 is the sum of term 1 and term 2. So that's 1/6 plus 2 over 12, but that reduces down to 1 over 6. And this gives us 2 over 6, which reduces to 1/3. S3 is the sum of term 1, term 2, and term 3. But the sum of term 1 and term 2 we already know to be 1/3. So we just need to add term 3, which is 3 over 20. We can make like denominators by multiplying by 20 over 20 and 3 over 3. So we get 20 over 60 plus 9 over 60, which is 29 over 60. S4 is the sum of the first 4 terms, but the sum of the first 3 terms we already know to be 29 over 60. So we just need to add term 4, which is 4 over 30. To make like denominators, we can multiply by 2 over 2, so we get 29 over 60 plus 8 over 60, which is 37 over 60. Finally, S5 is the sum of the first 5 terms, but the sum of the first 4 terms we already know to be 37 over 60. So we just need to add the fifth term, which is 5 over 42. When I am working with large numbers and no calculator, I sometimes like to factor the numbers down. 60 is 6 times 10, and 42 is 6 times 7. This way we see the common 6. So to make a common denominator, this first denominator is going to need a 7. So we can multiply by 7 over 7. Now we have 6 times 10 times 7. In the next denominator, we need a 10. So we can multiply by 10 over 10. And once again, we have 6 times 10 times 7. So we have a common denominator. 6 times 7 times 10 is 420. 7 times 37 was a little bit of a pain, but it turns out to be 259. So we have 259 plus 50, which is 309 over 420. Actually, that does reduce further to 103 over 140. Number 4 appears to be a bit simpler. S1 is just 1. S2 is the sum of the first 2 terms, which is 3 over 2. S3 is the sum of the first 3 terms, but the first 2 terms added up to 3 over 2, so we just need to add 1/4. We can make like denominators by multiplying by 2 over 2. So we get 6 over 4 plus 1 over 4, which equals 7 over 4. S4 will equal what we already got for S3 plus the fourth term 1 over 6. We can make like denominators by multiplying by 3 over 3 and 2 over 2. So we get 21 over 12 plus 2 over 12, which equals 23 over 12. S5 will be the total from S4 plus the fifth term 1 over 8. We can make like denominators if we multiply by 2 over 2 and 3 over 3. So that's 46 over 24 plus 3 over 24, which equals 49 over 24. Number 5 is written in sigma notation, so we have to generate the terms ourselves. Each term has the form -1 to the n plus 1 power over n factorial, starting with n equals 1 and then increasing by 1 each term. The exponents simplify to 2, 3, 4, 5, 6, and so on, and then -1 to an even power is +1, while -1 to an odd power is -1. So now we have this. 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, and 5 factorial is 120. And now that we have the first 5 terms, we can find the first 5 partial sums. S1 is just the first term, and S2 is the sum of the first 2 terms, which is 1/2. S3 will be the result of S2 plus term 3. We can get like denominators by multiplying by 3 over 3. Then we get 3 over 6 plus 1 over 6. This is 4 over 6, which reduces to 2/3. S4 will be the result of S3 plus term 4. We can form like denominators by multiplying by 8 over 8. So we have 16 over 24 minus 1 over 24, which is 15 over 24. This reduces to 5 over 8. S5 will be the result of S4 plus the fifth term. That gives us 75 over 120 plus 1 over 120. So that's 76 over 120, which reduces to 19 over 30. For the next 4 problems, we are being asked to verify that the infinite series diverges. In other words, we know that the series diverges, but we have to prove it. In the previous video, we learned one way to prove that a series diverges. It's called the Nth Term Test. You start by considering the limit of the rule as n approaches infinity. If the limit equals 0, that tells you absolutely nothing. However, if the limit does not equal 0, that proves that the series diverges. Again, this is the Nth Term Test. So far, the Nth Term Test is the only test we know, so we're going to use it on every one of these problems. For the Nth Term Test, we start by considering the limit of the rule as n approaches infinity. Since 1.05 is bigger than 1, the absolute value of this number will keep getting bigger and bigger as n gets bigger and bigger. Therefore, 4 times this number will keep increasing in absolute value as n increases. So already that tells us that the limit does not exist. On top of that, the sign will keep oscillating back and forth between positive and negative as n changes from an odd exponent to an even exponent to an odd exponent. I'm going to put this next bit in red for emphasis. It's not enough to say that the limit does not exist. What matters is that the limit does not equal 0. So put this in parentheses. Does not equal 0. We conclude by saying, so the series diverges by the Nth Term Test. I put this last part in red to emphasize that you have to state by name which test you're using. A proof of convergence or divergence has 5 parts to it, and you must include each of these 5 parts if you want to get full credit. We have to have a setup, a result, the significance, the conclusion, and the test. The limit is the setup. When we said the limit does not exist, that was the result. The important part of the result, or the significance of the result, was that the limit did not equal 0. This led us to the conclusion that the series diverges. But the tiny proof is not done until we name the test that we used. For number 10, we will once again start by considering the limit of the rule as n approaches infinity. As n approaches infinity, the only terms that will matter are n over 2n. So for the limit, we will ignore this 3. But then the n's will cancel, and we end up with 1/2. So that's the limit. 1/2 is the result, but the significance is the limit does not equal 0. So the series diverges by the nth term test. For full credit, make sure your answer includes the setup, the result, the significance, the conclusion, and the name of the test you used. For number 11, the setup is the limit of this expression as n approaches infinity. The 1 won't matter as n approaches infinity, so the original limit will be the same as the limit of n over the square root of n squared. Be careful, the square root of n squared is actually the absolute value of n, not just n. But as n approaches infinity, n is positive, so the absolute value doesn't really matter. So we get the limit of n over n, which is 1. Feel free to do all that in your head. So we have the setup, and now the result. Don't forget the significance, which is that 1 does not equal 0. So the series diverges by the nth term test. Don't forget to mention the test you're using, and this process will be a lot more interesting once we've learned a few more tests. Last one, what is the limit as n approaches infinity of n factorial over 2 to the n? Individually, the numerator and the denominator are both approaching infinity, but they are not approaching infinity at the same rate. If the numerator is growing faster, then that means that the overall value of the fraction is getting bigger and bigger, and the limit does not exist. If the denominator is growing faster, that means the denominator is getting bigger and bigger compared to the numerator, so the overall value of the fraction would be getting closer and closer to 0. We use the acronym FEPL to help us remember which expressions grow faster as n approaches infinity. FEPL ranks the different types of expressions from faster growing to slower growing as n approaches infinity. In this case, we have a factorial expression in the numerator and an exponential expression in the denominator. So according to FEPL, the numerator is growing faster than the denominator. Since the numerator is getting bigger and bigger compared to the denominator, the overall value of the fraction is just getting bigger and bigger. You could say the limit is infinity, or you could say the limit does not exist, but don't ever put an equal sign in front of infinity. What's important about the fact that the limit does not exist is that the limit does not equal 0. That's the significance, so don't forget to include that. By the way, notice I always put not equal to 0 in parentheses when there's a DNE in front. Never put DNE equals or does not equal anything. DNE is not a number. So the series diverges by the nth term test. One more time, for full credit, make sure your answer includes all 5 parts: the setup, the result, the significance, the conclusion, and the test.